The TDA, developing people, improving young lives.
Quadratic functions and their graphs are notoriously difficult to teach in a way that sustains students' interest. So here at Henry Court Community College in Fareham, they're addressing the problem by different departments working together. So the school's maths department is working with the PE department, and with the design, technology and science departments, together with the IT department, to make quadratic functions easier to understand. One real-life example of a quadratic function is the trajectory of a projectile. Henry Court is a specialist sports college, so it's natural to turn to the PE department for a source of suitable trajectories. The students use a video camera to capture their attempts to get the basketball in the net. And these are some of the videos they shot. The next step is to import their video clips into movement analysis software.
Yeah, we'll close that clip and we'll load it back up.
Using this, they mark the ball's position in each successive frame of video every 25th of a second.
What's happening is the ball's going closer to the top.
Slowing down.
It's slowing down, which is why the dots are a lot closer together. Yeah, because the ball's slow right down as it gets to the top there. Okay, and what that will do is we can then paste that into Geometry Sketchpad, and then we'll have a look at the graph of your basket.
Now the picture's in the dynamic geometry software, they calibrate the grid of the graph to match the known dimensions of the scene.
Yeah, so how far away from the basket were you when you shot the basket?
5 metres.
5 metres, so you need to change the grid to make it 5 metres wide.
That's on 5.
That's it, that's on 5, excellent. Now, how tall are you, Alex?
164.
So you're 1.64 metres tall. Excellent.
Meanwhile, in the design technology department, the students are working on another source of projectile trajectories.
They're building ping-pong launchers, and the idea is the ping-pong launchers can try to travel a distance of 3 metres to get the ping-pong ball into a bin. The way it operates is that they use these kits that are already assembled, and these kits that are assembled have 2 motors that work in opposite directions, and they have to wire them up to operate from a battery and use the frame that we've given them to design their own way of getting the angle changed so that the ball can travel through the air at different angles.
With adjustments to the angle and the speed of the motors, they can create different launch paths and sometimes get the ball in the bucket. The ping-pong videos are also analysed and their trajectories plotted, ready to tackle the maths.
Right, we're going to spend today looking at graphs, and in particular we're going to look at quadratic graphs.
Maths curriculum leader Mike Hartnell starts this Year 10 lesson by reminding the students of the work they've already done, tracking the trajectories of table tennis balls and basketballs.
There is Stuart's basketball. That's his trajectory there. And all I want you to do is match the graphs to your particular basket, all right? It's not easy, chaps, I will say that, OK? Right, off you go.
The students get started on this topic, one that's not easy for pupils or teachers, by importing their images into the dynamic geometry software and using it to plot a quadratic function that matches the flight of their ball.
Now we need to make it about there.
About there.
So it's about 3.4.
So plus 3.4. Right, that's the height. Now we need to bring it across a bit.
How do you bring it across?
The purpose of this session is for the students, by trial and improvement, to get a feel for how the various coefficients affect the shape of the graph. What makes it fatter or thinner, higher or lower?
We need to make that fatter. No, we don't.
Thinner. Take away the minus, see what happens then.
It goes up and down.
How about then, put the minus there.
Okay.
Oh my word, that didn't work.
Try 2.7.
That's 3.
Right, it's very close, isn't it?
Yeah.
Right. What else do we need to do at the moment?
Make it a little bit wider.
Yeah, it just needs to go a little bit shallower. Yeah, a bit more of a fatter curve. So how are we going to do that? What do we do to change it to make it fatter?
The 0.5.
Yeah.
Right, so what do we need to change it to make it slightly fatter?
0.6 or 7.
After the X. 0.4.
Right, you're saying 0.4, you're saying 0.6. What do you reckon?
I know.
When we had a bigger number, what was happening to the graph when we had a bigger number?
Oh, it got bigger.
You got steeper, yeah?
Yeah.
So we actually need to be smaller than 0.5. Right, you got the idea of it?
Yeah.
Right, I'll leave you alone for a minute and see how you come out with. So you're very close to that. Excellent stuff. Right, so how could we change it so that we sort of brought it down a little bit? What could we do to do that?
Change the 3 plus 3.5.
Right, so change that a bit now. Start tweaking this bit.
2.5.
It's brought it down, but it's brought it down again in that sort of direction, yeah? So you can see what's changing whenever you add on x's or whenever you add on numbers. You can see your graphs are completely changing. Okay?
Okay, thanks. Right.
This graph is a very close match.
Yeah, it's pretty complicated. Minus x squared divided by 2.35 minus 1.2 plus 2.25x plus 1.78. That's what we got. It could be simplified, but there's a few pluses of two separate numbers which could be added together. But other than that, it's done. Well, to make it shallower, you divide it. To make it from a u to an n, you times it by minus x. And to make it go across, you plus a number, something x, or minus. So now we're going to move on to those ping pong ones, like that. Well, we've started on this one, and it's not very successful so far. But we'll work on it.
Right. I think you've probably found that actually quite difficult. All right, it's not quite as easy. You go for one thing, it suddenly seems to work, and then all of a sudden you change something else, and it doesn't quite work. And a lot of you were just, in the end, struggling with the numbers there, not really knowing how to get on. But quite a few of you actually sort of started to work out what would happen when you did things. So something like Mike's basket. How are we going to get it to a point where it looks like it might go on the graph? What do we need to change? What sort of things am I going to put in there to change it round?
Minus x squared.
A minus x squared. Let's go and put in a minus x squared quickly then. I want a minus x to the power 2. Right, my minus x squared graph is right down the bottom there at the moment. Does that look like that's going to fit on that dot? Is that the same sort of shape as that graph? What do I need to change? How can I tweak what I've got there to change it round?
Would you plus, to get it?
To get it fatter. Yeah, let's get a fatter graph.
Would you plus, like, 2x?
Plus a 2x. Is that going to make it fatter by plusing a 2x?
Divide it.
Divide it by what sort of thing?
3.
Divided by 3? So what you're saying, the x divided by 3? Something like that? So we've got x squared divided by 3, yeah? See what that sort of does to our graph. Definitely made it a lot fatter.
It's too fat.
It is too fat, so come on in. How am I going to make it less fat then, Holly?
Decrease the number. So not decrease the 2. No, the 3.
So the 3, so what would I change it to?
1.5.
Change it to a 1.5?
Or would that make it even bigger? Oh.
Let's have a look.
Okay.
Let's change it to 1.5. It is slightly fatter.
That's too
Well,
small.
it's thinner than it was, in fact, than we started with. Probably still a bit too steep for what we've actually got there. So, should we try 2? Yeah? Seems like a fair thing to try. Try 2. How am I going to shift it up and about?
Would you plus an x?
Would I plus an x? So what difference does plus and an x do? Okay, it sort of moved it diagonally across. Okay, we might need to push it up a little bit. How are we going to push it? Perhaps up. What do we need to do to push it up?
Add a number on to the end.
Add a number onto the end.
Yeah.
What sort of number would you like to add on?
1.
What?
Yeah.
Pushing out. Do you want to add on some more?
Yeah, probably 1.5. Oh, a bit more then.
What would you like to try now?
Go for 2.
2?
Yeah.
Okay. It's getting there. What you're doing is you're trying these different things, but you're changing 3 things all the time. All right? You're changing what we do into the x squared. So we've not only put a minus in front of it, we've also halved it. We're changing the x's we're adding onto it, and that's making some sort of impact. It's pushing it diagonally. And then we're also changing this bit on the end, this 2. What we will go on to look at is the impact that this has and this has on the graph and how it shifts it around. because I think at the moment it's very much a, oh, if I do this, oh, I don't know what's happening, right? But it's giving you an insight into it, and hopefully I'll be able to explain to you why, when you change the number in front of the X, this happens, and when you change the number after that, this happens. Okay? Fantastic stuff.
So how did this project involving DT, maths and science get started?
We're actually quite lucky in the fact we've had a bit of funding to give us some cover to go to meetings and try and develop some of these ideas. Certainly sort of being able to talk to Graham about, well, hang on, are you building something there that we can use in maths, and talking to PE and saying, oh, hang on, you're doing this, and Sarah popping in and saying, well, hang on, the science in this is immense, and it's just being able to see what each other are doing and having the time to do it has been a real benefit.
This project is one that I've done before, with actually building these ball launchers, but to actually video the outcomes of what's happening and then to put it through the software which does the motion analysis, which is a completely new area. It requires the time to be able to get to grips with what the software can do. It just so happened that I was teaching this with a group that then picked the subject up with Mike, but it might not necessarily be the case.
No, that's
and it was quite nice for the students to actually see that linking together.
That is, in a perfect situation, they would have made it in DT, done a bit of the video clips, come to me, plotted the points on it, had a look at the graph, and then gone to Sarah and worked out and said, oh yeah, this is why it works like that. I mean, it would be really good if that happens, but you know, you're relying on the fact that they need time to make these machines. I need time to teach them some of the backgrounds of what they need to do for the graphs, and Sarah would also need time to teach them some of the basic science behind it. So there is always going to be a term or half a term perhaps in between them using it. But then in the same way, that acts as quite a nice refresher for them as well. If they've done it half a term and then half a term later they come back to the same bit of work they've done, but in science perhaps, then they're actually still refreshing the stuff they've done and revising it all the time, which is another crucial sort of element of our work.
What we're going to pick up and run with is looking at forces at Key Stage 3, looking at the profile of the ball as it's sort of going through the air, and we can actually plot that quite nicely. Key Stage 4, we're going to start looking again at forces, but more speed time graphs, acceleration. So we're going to look at it in that aspect as well.
And how do the students respond to the project?
I think one of the things this particular project's brought out is it's given them this desire to learn it. I think a lot of the time when you're teaching them quadratic graphs, it's not the most interesting of topics we have to study. I mean, it's fascinating for a mathematician, but for any other person who's just sitting there GCSE, there is no reason why you need to expand or factorise these brackets. By sort of involving them in a bit of their own PE lessons or a bit of their own DT lessons, all of a sudden there's this, oh, why is this happening? How is this happening? What's happening? Can I help myself? Can I solve this for myself? And it's certainly created that want to learn, which I think is important. And the number of comments we've had going, oh, we did that in DT and now you're going to use it in maths, and I didn't realise the two were connected. And the kids start getting out with this idea that for an hour they're doing DT, for an hour they're doing science, for an hour they're going to do some maths, and instead of that they're doing, oh, hang on, we've got to do a bit of everything everywhere, and everything all seems to tie in somehow. And I think that's important to sort of see some of the links, and certainly when you're trying to do some understanding of things, I think they need to see some links between subjects. So that's been really quite nice, I have to say. We've all enjoyed that, haven't we?
It's been good.